Okay, please take your seat. We are going to start again. So just some motivational speech. Now we go again into the statistics, starting with some slides from Knut, some new topics, but also catching from yesterday and so on. And I really want to underline, suggest, warmly recommend to follow fluidly as much as possible this session. It's morning, so you don't have excuses that you are tired and so on. Gianni Carugno scrambled our heads for a while, but we had a coffee break and now we can come back. Also, during the hands-on session, if you don't feel comfortable in doing the exercises by your own, it's fine for us if you group with another mate and you do it together. The important point is that you discuss and you try to solve everything because, again, to me, to us, it's the real way to understand and make some robust knowledge that can last for a while. The slides are there and also the exercises. So I think we can start and of course we will. Okay, I can help you with the timing. But we conclude at 10 past 1 p.m.
10 past 1.
10
Okay,
minutes late.
got it. All right. Hello, everyone. Back to the grind. I think it's possible that yesterday's exercises were perhaps a little bit underexplained and overambitious. That's okay. We're all learning people. So I put up here. If you go to yesterday's agenda, you can find this exercise sample solution, where I put up like my attempt at a quick solution. Let's just quickly look through that now. So the beginning was just some propaganda about always trying to use these vectorized ways of generating random numbers wherever possible, just because it's much more efficient. It's going to make your life much easier if you can get an answer in a minute than in 10 minutes. I mean, really, like genuinely, just for everything with software, if you can shorten the time between the time you press the button and you get an answer, whether it's roughly correct, it's going to help you immensely. So I genuinely strongly recommend you trying to make sure that at least the first time around that you try it, you get an answer out quickly rather than getting a perfect answer first time around. Anyways, so when we get to the test here, for the central limit theorem, this is a bit too small. Here. So for this guy, you can start, or hopefully, yes, go ahead. Yes, left. Let me move my computer also so I can scroll it. There we go. So for first try, I just put in some binomial distribution because it's very discrete. It's very unlikely continuous distribution. And when you look at it, if you squint from far away, it looks a bit Gaussian already. However, you can see, so this is discreteness that you would, if you designed a very clever goodness of fit test, perhaps a goodness of fit test that just checked are like my number randomly distributed in sort of the decimal place, then you would immediately see that this doesn't work. Here's it. Another example that I kind of liked was the exponential, because the exponential starts from 0 and then decays. It's just e to the minus x. And so this is going to be very asymmetrical for low numbers. If you add up quite a few of the numbers, so here I add up 10,000. You can see you define your distribution from sci-fi.stats, and you just get out. So this is why it's nice to use these vectors. You can just get out a matrix of number of summands times number of choice out of this immediately, and then immediately sum along the 0th axis to get all of the sums. No need for no need for loops, etc. Yes.
Is there any pros and cons for NumPy or SciPy random number distribution functions? Is one faster, is one better?
I don't know of any in general. That hasn't been the thing that has been limiting me. I like sci-fi.stats just because you have more distributions with more access to different test statistics, or not test statistics, sorry, but different variables for it. Now, the numpy.random is just to generate random numbers. These distributions also give you the PDF, the survival function, the log PDF. So it's very nice to just have everything in there, and you just use that until you find that this is the thing that's limiting you in processing time. Yeah, and then what I'm afraid I should have just instructed you guys, but you had to find it on your own, was that when you start adding these numbers, the mean starts going away from 0 and the variance starts going away from 1. And so,
Knut, I'm sorry.
yes.
Can you please share your screen on Zoom?
Sorry. I thought it was, oops. Okay, good. Sorry. The mean starts going away from 0, the standard deviation starts going away from 1. So you have to rescale this before you start trying to test out the shape. Otherwise, it's just going to say, you're getting a lot of numbers that are 12 or something, and then that's clearly not from a 0, 1 Gaussian distribution. But this is a little bit askew. If you look at it from a little bit far away, you can see, here it's always a little underdense, here it's perhaps a little bit overdense. And so this is where you can start testing. Not just rely on your eyes. And you have these different suggestions for goodness of fit tests. Some of them are built in not quite straightforwardly if you don't have an immediate impulse to start looking for them. But if you do, then you can start looking in for example, SoUP.stat, it has the KS test built in. You just apply it to your data and you get out a p-value. So a number that says how well this fits with the reality. In this case, this is quite low, so this would reject the fact that this data comes from a normal distribution. This is just one realization. If you start doing this for some 1,000 distributions, then you see this kind of distribution. So this is the p-value here and the probability density here, and you see when you have something that isn't Gaussian, but mimics a Gaussian, you still have a lot of p-values that start bunching up at 0, which means that this is now a test that is distinguishing between a real Gaussian and this distribution here, right? Because they start getting more and more extreme. They start saying, no, this doesn't work, this doesn't fit for many of the cases. Although you have many that also say, no, this is a fine distribution, this agrees. So this is what we talk about when we talk about a test being able to distinguish. It's not that it will always be able to, but that the distribution of the test statistic or the distribution of the p-value will start bunching up to 0. It will start pulling these distributions apart. I tried also with the chi-square test. Here you see this is the chi-squared for the 2 different distributions. You can convert that also into p-values, and you see here, actually, I was a bit surprised, but that's okay. That the chi-square test is a little bit better than the KS test. And you can do this also, well, cumulative is not important, but the important thing is you can do this now for a different number of summands. And is this not put? Okay, fine. So this is not run. If you run it yourself, you will now run this for different number of summands in your sum, right? So you will start summing just 1 number or start summing 5 numbers or 10 numbers, and you'll see how good is my test to distinguish these 2 hypotheses, and you'll get a nice power curve. And I can just spoil it for you. The power curve starts out at 1. If you have just a very non-Gaussian distribution, which you're having to summing just 1 exponential number, up to if you sum 20 or 30, then you have something that's very Gaussian-like. So you see it making this sort of standard S curve of power. Yeah, so check this out if you have time, or if you're bored on the train. And then let's start with the lectures for today. So. There, short summary again of yesterday. We model our observations with some statistical model. We can build these statistical models out of either some analytical, numerical, calculable PDFs, or we have to go to triangle to generate the distribution of our test statistic. But in all cases, when we measure something that is affected by randomness or affected by uncertainty. We choose test statistics that best distill the information from our measurements. We want something that is as much correlated with the thing we want to know from our distribution as possible. And we all often formulate questions in terms of hypothesis tests. We say, given the data, should we favor one or the other of our hypotheses? And a particularly important hypothesis test that we'll focus on a lot today. Particularly important hypothesis test is whether your data agrees with the distribution. These are these goodness of fit tests. You should always try to have at least one in your arsenal. And then today we'll focus on another very important test statistic, which is the likelihood. So I'll go through some example analyses with their statistical models, and in each case you'll see that there's a likelihood that describes how this measurement works. We'll talk about profile likelihoods that we only briefly covered yesterday, but I'll try to explain it in more detail today. And we'll go to one of the reasons why these likelihoods are so nice, which is that in many cases you can find a distribution that this likelihood follows, or the profile likelihood follows. And that allows you to save a lot of computational effort and answer a lot of good questions. And even if they don't quite fold, they will give you a first estimate. And then lastly, we'll talk about the look-alter effect, which is, very, hopefully in some of your minds after you saw the nice axiom plus that we had now before the break. So starting out with profiling likelihoods and nuisance parameters. So in general, it's rare that we have a completely fixed model for our experiment, right? We don't know exactly how many background events we expect. We don't know exactly the shape of the backgrounds. And so if we care about these uncertainties, if we want to be careful with reflecting reality, then we should add some parameters, some freedom in our model that reflects our uncertainty. And this is often parameterized by nuisance parameters. They don't have to. You could have models that just says, I have this model and this model. They're two alternative models for the background, and I don't know which one it is. But if we want to include this in our calculations, it's almost always nice to be able to attach a parameter to our uncertainty. And so these are the nuisance parameters stayed out throughout the presentation. And we denote the global best fits for the likelihood, so the maximum likelihood estimators with S hat, theta hat. However, we'll also want to test alternative hypotheses, right? We want to test, is our signal 0, is our signal 5, is our signal 10? In those cases, we call those conditional fits, where they're fits that you do for a certain signal. And in those cases, we put both of the hats on theta. So this is an example here from Monton. On the x-axis here, you have the signal expectation. So this is the number of WIMPs that you're seeing in your detector. In this case, I injected quite a few of them, you see, because you can see here that the maximum likelihood or the minimum negative log likelihood ratio is here at around 60 something. Well, here we have the electronic recoil expectation. So that's the dominant background in the experiment. And you see here the maximum likelihood estimate again is about 330 or 340 perhaps. However, you can also now start profiling this, right? You might ask, well, I want to test my hypothesis that the signal is 140. Now, it might be some theorist who wrote a paper that says the signal really is 140. That's the most important model. And so to test this one, you would then find the conditional fit here, and you will find your theta hat. That is the best fit signal for the best fit background for this signal, which is about 280. And you see here also, in this case, they're clearly anti-correlated. If you start pushing your model to have more signal in, it will react by starting to decrease the number of background events just to be able to accommodate to fit the data as best as possible. And again, why this is important, why this is really important to have these nuisance parameters is because our likelihoods, and in particular the correctness of our results that we present, they depend on the model. If we get the model right, then if we get the result right, that's an accident more than our skill that made it so. So we typically always include uncertainties on background rates. The distributions are a bit more tricky. This is an example from Monton again. Sorry for using so many examples, but a lot of plots lying around that I haven't used. So this shows here, in this region is where we expected WIMPs. So this is looking at, here is the ER band, and here is the WIMPs. So you're looking at this guy along this axis here. And you see here, we added a nuisance parameter that allowed our backgrounds the tail of our background that stretched into the WIMP region to either have a lot fatter tail here or a lot slimmer tail. So this was then, instead of saying, we know that it's this guy here in the middle, we added a nuisance parameter that allowed our data to choose which model is the best. So that you have some freedom to accommodate mistakes in your background. For Xenon Anton, this was actually replaced by more careful goodness of fit tests, because that's the alternative, right? That you can think of, well, if you're really, really certain that your model is quite well fitted, you can skip some of these shape uncertainties, but that's the general motivation. Okay, So, first example of a real life likelihood. We saw yesterday from Julia's presentation that DarkSide 50 has this excellent background to signal discrimination. So they can choose a region where they have a very low background estimate and a pretty good number of the total signal contained. And so counting experiments, they might seem to some extent very simple, no? Because you typically just have a Poisson with the number of events given your expectation for background and signal. However, there is no limits to how difficult it could be to estimate your expectation for the signal. Getting the acceptances right up here can be quite important. First of all, it is quite important, and it also can be quite difficult. And also, if you're doing this, you have to be really certain that your background is zero here, not nearly zero. No? If you see an event here and you committed yourself to saying my background is zero here, then you will always make the infinite sigma discovery of dark matter. Based on one event. So you really want to get that number right, because it can be quite dependent on it. On the other hand, you might also do a counting experiment if you have no way of distinguishing signal or background, right? If you just have some events and you can't tell at all if they're signal or background, then you would also do a counting experiment, right? So it's something that works in both extremes, but not somewhere in the middle. Because often these shapes do matter. These are some examples for xenon 1 ton, and you can see here, this is the fraction of signal versus fraction of background that is included. So you see here, as you start including signal, you get more and more backgrounds, but these are not the same, all of them. No, this is here, the dashed line would be if you have no discrimination, but all of these are like power curves, right? These are like hypothesis tests that show that, for example, the accidental coincidence or the sevens are much more signal-like than, for example, the ER distribution, which is much more only included if you start including all of the signal in your region. However, we don't use these summary plots except for just to look at how things are and get a feel for the distribution. What we actually use are the full shape distributions of our search. So the simplest kind of way of assuming a shape is what you would do if you were, for example, doing a directional dark matter search. Or if you were doing indirect detection, where you can point at something where dark matter is, and then you can point to somewhere where dark matter isn't. Or indeed, if you're a nice axion experiment and you can turn off your magnet, then in all cases you might be interested in doing these on-off likelihoods. No? So here, you're not just including a Poisson term for your science search, where you expect signal, but you're also including some Poisson term for your calibration data that then lets you constrain the background via this number of calibration events. And then you have to model with alpha, you have to model how much more background you expect in your calibration versus how much more background you expect in your search region. So this is an example from indirect detection. You can see they do one look at where dark matter is, and then they do 1, 2, 3, 4, 5, 6, 7, 8 looks at where dark matter isn't. And so here they would say in this Poisson, they would put in alpha equals 8 here and say, okay, I saw 80 events at my background events or in my background region where I expect 8 times more signal. So my best estimate for the background in the science region is 8 events. Now, of course, if you then see something there, then you will have to balance, that background estimate from what you get from the actual science region. Another version with bins are bin likelihoods. If you have quite a few events in each bin, you can do, as we'll see later now when we get to asymptotic distributions, you can assume nice asymptotic distributions of your test statistic if you have more than roughly 5 events per bin. So this makes a lot of things much easier. It makes computation quite easy when it comes to visualization and units of fit. It can also be that if you have a lot of events, if you have hundreds of thousands of events, it can be quite challenging to do an unbin fit to all of those and compute the PDF for 100,000 events instead of binning it into 100 bins and then just computing your test statistic based on that number of events in 100 bins. And this often works very well. If you have a resolution that is quite a bit bigger than the bandwidth, you will hardly lose any sensitivity at all by just taking your data here, in this case in different analysis spaces, and then just boom, 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 put them into bins and compare them with the model, and you get a result that is well performing and that can be well explained also to people. Oops, all the way around. And then lastly, we get to what at least the xenon experiments started using, which are unbinned likelihoods, in which case you compute the PDF. So then you start talking about continuous distributions here. Here you see different background distributions and the signal distribution for Xenon and Anton. And then you want to compute the PDF in each of these points. And one of my main enemies in life are these pies here. These are point samples of the PDF. So these are not saying something about the event. They're the event saying something about the PDF, which is that the PDF that was sampled in this point have these components. So, for example, if you sample an event in this place, then that PDF there has around 50% of the win for the best fit. Now, never invert that into saying that this event is 50% likely to be a win. But what that shows you is that the total likelihood here is a sum of these little estimates of the PDF in each of these little points. You see here, the likelihood you have the signal distribution and the background distribution, you weight it by the expectation values for the signal and background. And then you have a product of all of those probabilities. And you add also a Poisson term in front to account for the counting. And that gives you these big unbinned likelihoods. They will give you better performance. Sort of in general, if you got the right model, they will give you better performance than the binned distribution. At least if you have few enough events that you couldn't really bin them well and still be below the resolution. And then a very nice feature with all of these likelihoods and with statistical models in general is that you can compose them together, right? If you say I did a measurement here for my science data, and then I did a calibration measurement, and then someone did an estimate of this background, you can add all of these together to make a total statistical model. And so for example, here for these little Xenon experiments, you have the science search data, which is the data you take when you have no calibration, when you have stable detector. And you add a term that says, I took this calibration data to characterize, for example, my electronic recoil band. You'll have a calibration that constrains the shape of the ER band. And you'll add also these different ancillary nuisance parameters, or constraints for the ancillary nuisance parameters. And so you will add, for example, a Gaussian that says, I think my accidental coincidence rate is this plus minus that. Or you say my radiodynamics, which was shared between the science runs, is 0.3 events per exposure or something like this. And then you can even do this for multiple science runs. You can combine different experiments the same way. So for example, the Xenon and presumably now the LZ first or second science run, we're all combining results for separate science runs. Right? So then you just multiply together the likelihoods and you get one big likelihood that you can use to do your inference. Right. So what is so nice about all these likelihoods? It is that you can apply, or one of the nice things about the likelihoods is that you can use them to look up these, or you can compare them with these asymptotic distributions, which is a massive shortcut if you're careful, or if you're lucky, which is that the log likelihood for a number of Gaussian distributed numbers has the same form as the chi-squared formula, or in particular, the log likelihood ratio here. So you see, this is the -2 times the log of this is the likelihood with the hypothesis we're testing. Right here, we're testing that the signal is S. Oops, this should be thetas. Please disregard that these are S's at the moment. So you're testing that the hypothesis is S, and you get the conditional best fit theta. And you're comparing that with the global best fit. Right? So you're saying how much worse is my hypothesis that I'm testing to the global best fit to my data. And it turns out that you have a couple of conditions here that you need to fulfill that we'll go through in turn. And if all of these are fulfilled, then you're able to rely on this thing being chi-square distributed. So the first one, or now we're going to make an example experiment to investigate these different conditions. So let's think of something like these dark side 20K or dark side in general searches where you have some background. Let's imagine that they didn't have zero background here. So we'll say we have a couple of parameters. We have a signal here, and we're estimating an efficiency to see this signal. We have perhaps some cuts, we have some detection efficiency. So together we have some fraction of times that our event will actually be seen there if there was a real event in the detector. We have some fixed known parameters. I'm going to assume that we know the background in this region and that we know the uncertainty of the efficiency, so that the uncertainty is measured with some Gaussian distribution. And we have two data points. We have the number of events that we count in here, and we have the efficiency estimate, which is important. Note that when we look at this, we should look at this as we did an experiment, quote unquote, or we did a measurement of the efficiency. That's what we put in here in this term. That says the measurement of the efficiency is a Gaussian with mean the true efficiency and sigma the uncertainty. And we have here what's on that says this is the number of events we expect given signal and efficiency and background. This works very well if you have a lot of events. If you add 20 signal events and 20 background events and you have a nice 10% uncertainty on your efficiency, then you'll have something that looks really quite like a chi-squared. This is great. Now you can save, tens, 20s of hours of CPU time. However, we go back to our requirements, right? Which is the first one. We have to have sufficient data, quote unquote. What does that mean? Well, in general, this distribution, what is called Wilks theorem, that this will approach a lot like chi-squared, is only really guaranteed in the limit of infinite data. However, we're often very lucky, and infinity happens way sooner than we think. For example, Poisson predicting with more than circa 10 events. In many cases, you're already at Gaussian measurements, in which cases it holds immediately. However, if you have an unbinned likelihood, or you have rare event searches in general, you're often looking at very few events. So you really have to test this. It might not hold. And even if you have many events, if most of those events are not signal-like, then this might not hold. So you're looking for not just sufficient data in the sense of having 1,000 events, but having thousands of signal-like events, or at least some tens of signal-like events. Because otherwise, it turns out the likelihood will just look at the part that is signal-like. Now, that's a good and bad thing about the likelihood. We want it to only look at the signal-like events. But it means also that when we talk here about sufficient data, it really only applies to the signal-like events.
So basically what you're suggesting is that in order to run with the Wilks theorem, we can give up all the background suppression that we are doing, such that we have many next events over there.
Yes, if your one goal in life was to ensure that, well, I was out of a job and analysis for the Wilksian experiments was easy, then absolutely we should never have any radon distillation. We should make sure to have very low fields, so everything becomes smushed together, and then just do counting experiments. Exactly, yeah, neutron beta is horrible. Especially because neutron betas reduce the signal-like background, which is exactly what you want to have in if you want this theory to hold. So for sure, you should never try to remove backgrounds that you can avoid to remove.
Okay.
Yes, good lesson, everyone. So this is how these look like. This is now if you have a very low background, so 0.2 events, which you might have. That's a pretty common kind of statement that you would make in these rare event searches, and you can see this is by now very unlikely chi-squared. You have a lot of discreteness, which is fine. You can deal with this, but you have to deal with this by not using the chi-squared. Another thing is you need your values to be what's called interior to the parameter space. It needs to be so that you don't have a parameter right at the boundary of your parameter space. However, so a mental shortcut of this, if under the null or signal hypothesis, one of the parameters is best fit goes to the boundary some fraction of the time, say if it goes to the boundary 10, 20% of the times, then you should start worrying about this. So if your best fit signal goes to 0, 10, 20% of the time, or if your best fit efficiency goes to 0, 10, 20% of the time, then you really should start worrying about this thing. And in particular, for dark matter, because few of us have yet measured dark matter, we often look for a signal with just an expectation value greater or equal than 0. So this is a physical boundary, or unless you modify your likelihood to accommodate negative dark matter signals, then this will be a physical boundary for your likelihood that you need to accommodate. It turns out that if you're right at the boundary, you can accommodate it by saying, okay, half of the time I'm at the boundary and my log likelihood ratio is 0, and half of the time I have, this should be it is a half. And half of the time I have a normal chi-squared where my say best fit signal is about 0. So this you'll see a lot when people talk about discovery significance, because they're looking for a signal that is bigger than 0, but you're looking for the H0, which is that the signal is exactly at 0, and then in half of the cases the best fit will go below, or go below, which is just stay at 0, and half of the cases it will go above, and that will give you this nice formula for the distribution of the test statistic. And we see this can work quite well. In this case, you have a background of 40 and a signal of 0, and you're trying out the distribution of the test statistic if the signal really is 0, and you get a pretty reasonable, you see you're going down to 10 to the minus 2, 10 to the minus 3, and it's still a reasonably good estimate of the test statistic distribution. And in this case, the efficiency is also far away from its boundary. It would be a 10 sigma deviation for this guy to go down to 0. If on the other hand you say, okay, I want my efficiency, I really don't know my efficiency. It could be 1, it could be 2, it could be 0 almost. Then you're in trouble. Then this doesn't hold, because now not just the signal can go down to 0, but now also the efficiency can in some fraction of times go down to 0. That will also make numerical trouble for you. But the important thing here is now this guy no longer holds. Now systematically your test statistic distribution is unlike the chi-square distribution. Okay, then we'll get more into this at the end of the lecture, which is different values of the parameter must specify different models. If there are some parameters that are degenerate, which often happens actually in physics, because if your signal strength is 0, any signal parameter doesn't affect your likelihood, right? If you have 0 cross section, then if the wind mass is 6 or 25, it doesn't matter for your response. And so we'll get into how you square this with the low-Elsewhere effect. They should be nested, which is that H0 should be a limiting case of H1. That I think is almost always the case for us, that we say, okay, H0 is just set the signal to 0, it's just a limit of H1. But if you were to, for example, compare two separate shapes of backgrounds that are not within each other, then you might have to linearly add the models together or do something else to make sure that the models are part of one big model so that you can compare them in this framework. And then lastly, you really need, for these distributions to hold, you need that your true model is specified either under H0 or under H1. So it needs to be part of your total model space. We should be cognizant that this is probably never precisely true, and it's certainly not guaranteed. So you should try these goodness of fit tests. You should try, in particular, you should try goodness of fit tests that target the kind of mismodeling that you're concerned about and see how much it could affect your result. And I think it's the most important thing is how vulnerable your result is to the mismodeling. That's even more important than being robust, is knowing whether you're robust or not. So examples of when these might be used. Sometimes people recommend this paper here by Cowan et al. That set up a lot of different test statistic distribution or different definitions of the test statistic if you're doing discovery or if you're doing upper limit or if you're doing unified confidence intervals. I would recommend we can look at this tomorrow when we're looking at confidence interval. But in general, all of these can be seen as the same test statistic if you just instead replace these conditions by saying, I have parameter boundaries beyond which I will not allow my estimators to go. So for example, here, if mu hat is below 0, then you want this 0, but you can just say, no, I will not allow in my minimization mu hat to go below 0, and then it will solve the same problem as this guy.
So Knut, yes, again, a question here just to understand better. So the third one, the unified that you call, is basically the way to put Feldman-Kruzin in the language of
Yes.
the profile life.
Exactly.
The point.
Yes, we will have a lot of nice we will have at least one nice animation tomorrow about making this. So all of you can be super excited about nice animation. But yeah, in general, I mean, if you look at this, right, what this is saying, right, this is the normal profile like this, right? And this guy is just saying, yeah, if mu hat goes below 0, then you replace mu hat with 0. So this is again it's a parameter boundary. It's just a way of accounting for when mu hat goes below 0, and you can easily do that just by saying, no, I will not allow an minimizer to do that. So we have one last fun thing, which is now what if we're testing different hypotheses, which is another way of saying what if we have some parameters that are not defined under our null hypotheses. And so if you keep trying your luck. Now, in real life, this doesn't always work. If you keep trying your luck, you just get more and more in depth. But in physics, if you keep trying your luck, you will at some point find some significant upwards fluctuation. And so this is what's called the trial factor. You need to somehow correct for the fact that you looked for many different signals. You have many different tries at finding something. And so we separate between what is called local significance, which is when you pretend, or you, for calculation's sake, you just compute, if I knew that, for example, the Higgs mass was at 125.6, what would be my significance of finding it then? And then the global significance is, if I didn't know where the Higgs mass was, but I tried all these different masses, what is the significance of finding the most extreme example right here? So the simplest kind of way of looking at the look-elsewhere effect is if you have uncorrelated trials, if you're trying models that are completely uncorrelated with each other, in which case it's just a binomial, right? You either have something which is significant beyond a certain significance level or it isn't. And then you get, say, 3 sigma of 0.0027. But if you try that 10 times, it turns out, if you have a very small p-value, that approximately just is divided by the number of trials. So you often see this in some literature that they do this Bonferroni correction, they call it, which is just dividing the p-value by the number of trials to get your corrected p-value, which is an approximation if you have uncorrelated trials and you have small p-values. If you have large p-values, you don't really care about getting it correct anyways, because nobody is going to be excited about getting exactly the right level of significance for something that is anyways not significant. However, for us, it's often a bit harder because our results are often correlated. And so in those cases, you might either have to do TOMCs, or in some cases, you're able to use a clever trick, what Justin tells, which is that you can estimate your distribution here. Is this visible beyond the computer? Okay. Good. You can count the number of times your test statistic crosses a certain significant threshold, and that will essentially tell you like a little bit of, it's like a natural amount of statistics that tells you how often does this guy fluctuate above a certain significance level. And Gross and Vitals allows you to extrapolate from the number of times it fluctuated above a low significance level to how many times it's likely that it fluctuated above a high significance level. So that allows you to escape having to do TOMCs out to like 10 to the minus 5, 10 to the minus 6. However, I would also say, if you have a very significant discovery, it's very likely that your PI will just give you the computing resources to compute it out to 10 to the minus 7 anyways. You could see this with the gravitational wave discovery. They just said greater than 5 sigma because they just kept running TOMCs until they were able to characterize their p-value distribution out to 10 to the minus 7, and then they said, okay, that's good. We're not going to use more computing resources. But these are examples from liquid xenon experiments where you've probably often looked at this and wondered, why is this, or you were now explained by Julia why this is straight up here, right? This is just where the signal in the detector looks the same for all of these masses, which is to say that for all of these masses, it's essentially one trial, right? This is the same experiment as this experiment as this experiment. So this is why we just put in an equation here, so you can just extrapolate it up to however many TeV you want. But down here, you have a little bit of information about the shape. If you have a very low mass WIMP, you have an exponential that falls very steeply, then you will be able to tell that away from 30 GeV mass dark matter versus 200 GeV dark matter. And so this is some estimates of the different trial factors here. So here you have the local p-value versus the global p-value. And you see here, if you just test this part here, if you just test 50 plus GeV for a liquid xenon experiment, you're essentially doing just one trial. So here the minimum local p-value and the global p-value are exactly the same. While if you now add in the 4 GeV plus here, so this is TOMCs, which is why I was able to pretend that we can see dark matter at 4 GeV. But this then sees, okay, you have a little bit of an increase, but if you look at the scale, it's just a factor 2 or something in probability. It's not so many trials that we're looking at. And if you're looking at the most extreme, the most trial factor you can have in a liquid xenon experiment, this is if you have monoenergetic peaks, right? This is the detector resolution limit. You're trying to squeeze in the smallest nuclear recoil signal you can. And in that case, still, you're just looking at trial factor perhaps around 10 here between the minimum local p-value and the global p-value. In other cases, that might not be the case. Look at these axial layers. They have a very, very, very high number of fluctuations, which is just to say that the fineness of them being able to say, the axial mass is exactly this number is very good. They have a very good resolution. But it also means that they have to try a bajillion number of times here to see, is the axion here. So they have a very, very high trial factor that they need to contend with. So please, make that something to sort of adjust your expectation for different experiments. What kind of trial factor are they looking at? Something that related to trial factors is also you should try very, very clearly that you're not doing internal trial factors in your experiment before you're publishing, that you're not accounting for. So if you have very few events, there is a chance that you'll see something weird, and the fewer events you have, the more power each of those events are going to have to affect your results. So this on the right here is from Simon Montan, and this is the upper limit if you change the radial count, for example. Now, if you said after the fact, no, I mean, I don't trust our wall distribution out here. I think we need to change the count. And you can see you can essentially choose your own upper limit here within like a factor of 2 if you choose the different radial count, which is also to say that these experiments are very sensitive to small number of events. There are also experiments that many of them measure a lot of things about each event. And there are few events. So each of these events are somehow going to look extreme in some parameter space just by virtue of having measured, 50 different numbers about that one event, and you have just a couple of hundred events. All of these events are going to look somehow weird if you start interrogating them one by one without being careful. So this I would put up here that this is some kind of homeopathic poison. The fewer events you put into your experiment, the greater the danger is of doing these kind of online analyses. So what we do here in general in direct detection and in dark matter is we do either blinding, which is to say, first of all, you go through a lot of work to have your summary notes, to have a complete agreement within the experiment that you're ready to unblind. And then you look at your data here. This is the region of before unblinding here, where we were looking for 2 different signals here, an ER signal and a WIM signal. And then we first unblinded the ER range, and we searched for a signal here and didn't find anything. And then we unblinded the WIMP region and also didn't find anything there that wasn't just one signal cross fluctuation. Lux and LZ developed a sorting procedure where instead of hiding away this region, they instead add fake signal to this region, which you have to again be careful about, because as I said, you're measuring many different parameters about this distribution, so you have to make sure that the signal you're putting in is quite close to the real deal, to not then skew the analysis afterwards. But this has now been working, I think, for LZ, but you have to make sure, first of all, that it looks exactly like the signal, and second of all, that it's sort of pretty hefty salty. It should not be just one event that could look exactly like WIMP, because then it's not going to hide the actual result of the experiment itself. Okay, so that brings us to the end of the lecture for today. We have some exercise set that you can find on the agenda. For today, we have profile likelihoods in comparison with the asymptotic. So we start with gaining a little bit of intro, or I start with a little bit of an intro, just saying this is how I would go about doing function minimization, just so we have the same tools that we're working with. And then you'll define a simple likelihood, minimize that, and start comparing it to the asymptotic results. Good. And what we analyzed, we talked about how different experiments analyze things, how they define statistical models and likelihoods for their results. We discussed a little bit the profile likelihoods, and we discussed the asymptotic distributions, which things you need to make sure about your experiment before you can use them, and also how useful they are. And look at elsewhere effects and other dangers you need to make sure to account for when you're doing an analysis. Great. Questions before we start with the exercises? No? Great. Happy hunting for asymptotics.
We have about 1 hour
Yeah.
to get on, and ask around. Okay, don't be stuck. So if you're stuck,
Yes,
don't stay stuck.
exactly. Yeah. Set a timer. Really set a timer for 5 minutes, and if you're still stuck, lift up your hand.
Exactly.
Yeah, I've left my scarf.
Can I follow this one?
Sure.
Maybe it's That's copy everything. Okay, I will copy everything. Then I'll. Transfer.
Yeah, you don't need to go in. Then you do. Yeah, I think not that way. So we got that much. You post it. Yeah, it's like you don't want to go. Yeah, but I do that. They don't be right. You don't want to have this blame. But yeah, I wouldn't do too much. Explain. Is it for you? I use it anyway.
Because sometimes they add functions and then you can
That's what but the whole thing that's not much of a yeah, it's understanding like
yeah.
because if someone else on your computer, say someone else is not very much, if you haven't, but they might. Yeah, yeah. I would finish it in a certain episode. Yeah, that's right. Yeah. I don't know what second. Yeah, but I get in there. Yeah. Yeah, that's basically. Yeah.
Now you restart the current live, so you just restart the whole thing. Yeah, we just get all that and then see what happens.
Well, you can show. You put ground. Yeah.
I wonder if I might, can you, is there somewhere where it says clear, either self or something? Just clear all of it, is there something that says that? Right. I'll talk to them. And then restart the current. Yeah, just run the first cell.
Exactly, yeah. I'm advised. I was working.
But
It's like. So here and. No, I was working with.
Wait, so exercise one works with exercise two does not?
Oh, yeah. Yeah, yeah. That's a lot. Why asking me? Because you're not.
Oh. You'll do that.
This is where it's from.
Yeah.
Yeah, just a bit. Yeah.
That's true.
Yeah, I'm speaking to the
Excellent. Because there's not so much. You didn't even hear me.
So the numbers, the verification, they signal plus back.
telling them. That's okay, then it's fine, because also you get more direction, like, you know,
And what do you think about it?
So this is, so this is made with,
the first, I like the second one. That's not better.
It depends how formal it is.
You can not formal, you can second one.
See what's up. Yeah, let's go to my first. I don't actually really stop this year. I think. First is like. Yeah. Why not to leave it?
at least for me, we need to just live with that, but I'm actually trying to.
Oh, yeah, so you generate.
Okay.
Stuff.
Or you work in because of like sound. Yeah.
Yes. Yes, exactly. I you were using your statement. You don't need to like essay of what you say. Yeah, because at the beginning, because the price The name I just wrote.
They should.
So the mid price is.
This is the, you're the first, like, afterwards.
And so. Oh, I did. And so this is.
So all I said was like, okay. This is. It's me like.
Okay.
Like, really, there is a level of explain, like, sort of read the workshop. Yeah, I feel like, I feel like probably.
Because
It did have a lot to do for them, even though it couldn't do it before, it allowed me to find an idea to allow. Like, oh, let's try it, just something, but it couldn't do the proper, I don't do, yeah, because, yeah, I used to put it I have to actually count it, I really need to look at it. If you ask me, so she can like touch
Number one, when we get into organization.
And in particular, I think science, in particular, I think just like. But I shot it. It's true that if you want to also like production, you come back to the main. And the minimize. In many cases.
Second question, I don't understand. Generate under 18 to start generate function.
So you observe some.
So
We have some people in the floor. Oh, yeah. I love it. Like, he was really asked to take
I should run the next 2 minutes.
That's fine, as long as it's. And it's.
How many events? So I run the any event.
Like, change the table, half the day. And so he's a good for us, because we need to, like, he's got the destination, like, basically getting the version of. Yeah, well, no, you did do it. Conditions, fine, but and I thought the word that doesn't really, so you have to, so I can then, simulation of data, because it's like, oh, all the possible. And so I've got all the analysis to do, and so it's funny to do the one thing you do is avoid the time cut. So if you look at like take signals of the OD and take away signals of the TBC, find the time between the trigger and quickly, and usually more like so and so we can take like a timing coincidence cut, because what you get like time, you difference in time. There's usually a peak of one of each like put a window around it. It's quite easy. Anyway, so this is quite different. I think usually like changes and side operation of the trigger changes basically between the and so I was like, right, okay, you send me your time cut again. Like the new one, you know, he's like, all right, yeah, this is actually, I actually need this. I know, so I was like, you know what, like, look, the last bit of you like, I like sort of stuff like. The last bit of useful is because I have to do, so you're like, you know what, that's not hard, I'm gonna just myself, not going to like, oh no, that was your piece of I'm stealing it. I know, I did myself, I did the same thing, I compared, so I looked at the Windows gave me, and then 2 days, and then I overlaid. I thought it was like your motion. No, I've done the cuts, I've done the reset, I've done it again, and add it together. Yeah, so assuming the analysis, change the results, and I just actually write it again. But I spent a lot of effort trying to write it down, I don't think it's really deep. Basically every time you say something, it's like LD flag, so there's gonna change it. It's generic. So I think we'll do I think we'll be quite.
Right.
Yeah, well, I know you say that. And in the work. I mean, for one thing, it was. Okay, maybe that's on that. I don't think it would be able to handle it because it's take the license. So we are using energy full scale. Yeah, I think it's great. But that's what you have to maybe we can kind of we use this wasn't being in the next relationship. People that learn a lot about looking at, so we just know actually where we know that they're using so it's okay. And then we put because every time we have a file, things crash, it wouldn't be more data. We had loads of data files where we had like hardly events, so it was like, yeah, so I had to go into LD Mark. So I had to edit LD Mark, like the actual, like, anyway, LD Mark. It's so complicated. Yeah, literally, I was trying to submit Jake to see if the final wasn't actually going to like an election. I was having to say to you, but I have to get all the data, and I found out I was saying, I felt like forcing like one of the rare artists, it just died, and so I went in and every file, printing out whatever files and I share it like a crashed file and be like, oh, I was thinking about what you said. Anyway, I changed on the book, I pushed it, this one parameter, like, oh, you know how you like push it, like, you know, they could, yeah. Literally, who's like, who is it that we? I don't know, like, let's do more because of all but the first one version, like, go through all the check functions. So the second one, gets rid of line, like, I'm like worried about that. Yeah, I think they are. Yeah. That's great. Oh yeah, great. Yes, then gross for a while. So it basically just took us way too long to discover this background. It was like explaining all the aspects. Also, we had to find like cuts. I looked at profit of viewers and like, what are going to be the best cuts for every yeah, pretty much all the viewers secondaries. I don't know what it's about. Too bad. It takes a lot of me because I didn't really understand what you were doing. I mean, I thought it was reviewing, but I didn't really know much about it. Yeah. I didn't know. It's always the thing about like starting up, and it's like you have to just like learn all of it. Yeah. Like all of these properties, what's going to be like. Yeah. I remember like when I was doing now, yeah, it's like one of them, isn't it? Yeah, why did it take this so long? The list of viewers now, I literally can't like. Yeah. So now we can do everything again, like now to rerun it. So it's 24 minutes. Yeah. You are. I got one like. Some of those. Yeah, I wish I did one of my rooms. I've been one of my rooms. I guess it was down back outside. I never used like, oh, like, I don't do this for this. Yeah, we get quite. She's going into the I would like to leave you the fun. No, like, if I'm cold, it's gonna be don't know shit. 7 or 8 hours. Are you gonna do no, thanks so much again. The thing is, yeah, so that there was nothing. It's very good to be around. So you have to be yeah. 6 a.m. So I think 6 p.m. They haven't given us much anyway. Yeah, mine will take 2 hours. Yeah. Yeah.
You told me that.
Anything unusual. Yeah, it's a bonus. Yeah, I was looking at it. See, there was no place to be in there. Yeah, sorry. Because there was a little bit. Yeah, yeah, on you, yeah, because the worst bit was it was like, that one. Rejecting it, yeah, it's so funny, it's just bad. Let's turn that off. It's like, it's actually scary. Oh, right. Yeah. I'll be. I feel that they are to be, I'm glad it's not fucking last month. Yeah, now we're a bit of a Got to keep going. I don't really, yeah, it's like, that's last month. It's been going on. Just be like, yeah, that was like.
Sometimes it's more.
It's just like, she's done it twice, like, she's rocking a conversation. Having one, and then like, somebody told them, never talk to you, oh yeah, I'm studying the option. She's like, thank you for inventing the you're not currently doing it. Tell me how to go through it. I think the last slide. It's like, oh, this is how it's trained. It's like, they're like, oh, like, Ellie's the allergy. Things like that.
Oh, sorry.
Presentation. My research. The talent and my skills for my highlights. Criticism.
So I would know.
Right, or you have that recommendation, it's out from your.
Yeah, like someone like. Like, I want to see what was like, I don't need that. Yeah. I can put a section on the facility. Like, you give me close maybe photos on how you think that change. If I do well, I've tried to. If I was involved in this campaign, not necessarily with this job, but yeah. Yeah.
then it was going to do like
There we go. That's great. Why can't it
Or you do have interest.
First Friday, and like these my ambitions. Like that one. I don't think it's the last time. Maybe did what champion talk.
Right, so you want the.
Like then you don't. Really, okay, absolutely.
So the minimum is going to try many different values. So that means that even if he's use something about to compute inside the function. Minus 2 log. Right, and you can pass them in values here. And once you pass them in, you can so here you say A is there, B is there, you can change them. These are good values for A and B, they're not good values for B, because first of all, N is
It's like, you can do that right now. I'm like,
See. All right. Hello, everyone. We're approaching lunch. Make sure to ask any questions you have before. You can also just accost me after lunch about them. But if you have any immediate questions, please ask them now. If you have something you think will be good to discuss now in common, we can do that. Yeah. Otherwise, I was happy to see many just be very serious about getting this, about looking through these exercises. Thanks a lot for that. And yeah, see you in some minutes for lunch.
So,
Okay, so a few announcements, information while you are finishing before going to the lunch break. First of all, please, if it's not a problem, keep your T-shirt on or around. We'll have the third and last. I promise. Just before the possible session along the stairs in the castle. Okay, that's the last one. Second point, this is important for you in particular. On Friday, unfortunately, there is another strike. I will work. However, we decided to have the shuttle bringing you to Bologna back. Okay, so the starting time will be the same. Basically at 2:30, we will start moving down, taking the shuttle, and going to Bologna in the same spot where you have picked up. Basically, you can consider that. We will send around. Sorry, I guess it's important for you. Basically, you will arrive in Bologna earlier than what you have done with the train, leaving at 3:30 from Forlì, which was the one you were supposed to catch. Okay, I will write down the information and send also the email such that you can plan the trip better. Anyway, from our side, this is the best we can do to bring you at least in Bologna, and then I hope you can have a safe and short trip. Yeah, maybe for, yes,
Trip is still after lunch.
say it again.
The shuttle is still after lunch.
So the shuttle is there at the same time. So we will have lunch on Friday at 1:30, and the shuttle, and we will leave at 2:30. Okay, basically at before 4:30 you will be in Bologna. That's the, so as you were supposed to do with the shuttle to Forlì plus train from Forlì to Bologna. Maybe, yes?
I was just gonna ask, in the route, it says that we have to check out by 10:30, is that true, or are we able to go and get our stuff like after lunch before?
So for the checkout, you have to leave, the best is to leave right after breakfast, but you can leave your luggage at the where the accommodation is. Okay, that's the best. But I think we can come later to this. I will send around the information on the shuttle via email such that it's even clearer. If you have any specific points, come to me or to Roberta, the secretary. Okay. Third and quick, but I need Virginia to come here. Are you able to sing? Can you sing? So join me singing Happy Birthday to you. Happy birthday to you. Happy birthday to you. Back here at 2:30. Thanks, Knut. Did you get many?
I think today,
Questions around?
I think today it seemed like people were working quite straight, so I was happy.
Yeah, I also heard the noise of the fingers.
Exactly, it's productive noises.
I'll send this to you also.